Hi everyone, we're presenting our capstone project today called Forestcasting. Our team is called Pythia and our mission is to equip the public sector with analytics tools to enhance their decision making. Our app is called Forestcasting and it's a forest fire management tool for forest fire managers that provides them with accurate fire risk prediction and also a clear view of the possible damages in an area so that they can have a comprehensive outlook of a fire happening in a certain location, and that way they will be able to prioritize their firefighting efforts. Our database hosted on MongoDB. Our data pipeline and machine learning is written in Python and hosted on Google Collaboratory. Our backend is a Node.js server, and our frontend is written in React.js, and they are all hosted on AWS. So a forest fire manager would be able to log into our app, and immediately they're prompted to select a location. They can select a location by dropping a pin. So because I dropped a pin in a location in the United States, which our machine learning model currently does not support, I'm encouraged to look at the map of the supported areas. So this is all of Canada minus the territories. So again, I can choose any location in Canada and it'll be a valid location, or I can search for an exact address. So for the purpose of this demo, we want to show you guys a protected area to show how that affects the possible damages. Then the user is prompted to select a range of dates. So they can select up to a year, and let's do a week in August for now. The weather prediction, if it's later than a week, so further than a week from today, it will be using historical data in the calculation, because obviously up to a year we need to rely on historical data. Then the forest fire managers will be able to view the fire risk prediction for every single day in the range that they predicted. And because our research showed that fire risk is very heavily tied to the weather information, we have the weather information for every single day here. And you can see it's a relatively higher percentage. And this is obviously tied heavily to the temperature. Then they will be able to, on the right-hand side, view the possible damages that will happen in that area. The possible damages is a percentage that is relative to the minimum and the maximum damage that could happen in that area. So minimum 0% and maximum 100%. For this location, it's 36%, and it's obviously independent of the date. So at any time, at any point in time, if a fire was to happen, there would be a 36% chance of possible damages. The possible damages is calculated using 3 different factors: the vicinity, which is the population and the distance to the nearest city to that location that's selected, the protected areas that are near that location. So here we have 3 of them, and that's why the score for the protected areas is higher. And obviously the tree coverage information as well, which is lower in this case. If a forest fire manager cares more about one of these factors, for example, protected areas, they can increase the weighting, and that will obviously impact the algorithm, and they will be able to prioritize their efforts accordingly. Finally, we have the ecozone information here. So some information about the ecozone and some historical data. To give you guys a comparison, this is a prediction for a week in March in another location in Alberta. So again, ecozone 9, but you see the fire risk is much lower because it is in March and the temperatures in Alberta in that location are very it's very low, so the chance of a fire happening then is very low. And the possible damages, again, we have the Banff National Park of Canada close to this location, so that is heavily driving the score up. And then in this case, the tree coverage score is also higher. And finally, we also have some information about the model here if they wanted to know more about how the fire risk is calculated. And other than that, they're able to generate a PDF of the results in order to keep it for their own record keeping and decision making.
Great, thanks Shima. So it's Sam here. We're going to go over how we generated all the data to calculate that damage score that Shima was talking about. So the first piece of data that we gathered was the tree coverage. So the tree coverage data was gathered through the Google Earth Engine API and mapped to our proprietary grid system. The second metric that we had to gather was protected areas. So these are things such as national parks, critical habitat, historical sites. So each grid now has a number of protected areas associated with it. And then finally, we pulled from the Wolfram Alpha API so that given a location, we can find the population of the nearest city and the distance to that city. Now, when we wanted to combine these three values, we had to do some scaling since they all had various numerical ranges. So we did a basic min-max scaling. And then for protected area data, we had to do a little bit more of a normalization because we wanted the jump from 0 to 1 protected area to create a larger score change than the jump from 6 to 7 protected areas. So we applied a logarithmic normalization, and you can see in the bottom here that the output graph on the right gives a more of a normal distribution than the starting graph on the left. Once we had these three values scaled and normalized, we were able to combine them in a weighted sum that you saw during the demo is configurable to the forest fire manager's needs. I am now going to pass it off to my colleague Tharmiga to talk about the machine learning pipeline.
Hi, so I'll be talking about our fire prediction data pipeline. And initially we started with our grid creation. So this is where we divide Canada into 20 by 20 kilometer squares using latitude and longitude. And then we map weather stations to each of the specific grid locations. Then we take our fire data and we map it to the same grid. And then we go ahead and get ecoregion information and map that to the grid location. This is important because ecoregions have different characteristics that can impact the risk of a forest fire happening. And then we got daily and hourly information and mapped it to the grid as well. And then we get historic stats, which helps us relate previous fire activity in a location in order to use that to predict the risk of a fire happening today. We use an alpha distribution to fill in any missing duration values that we have. And then we join the fire, weather, and ecoregion, as well as the historic statistics data into one data frame. And now I'll hand it off to Ivan, who will be talking about how we continue from this data pipeline into the machine learning model.
Thanks. So the last step before machine learning is the pre-processing of the data. So we approximate null values using other data. We analyze and create new features, and we use a sine and cos curve to make months and days take on continuous values. For the actual machine learning aspect, one of the challenges was dealing with an imbalance. So we downsampled the majority data, and we used a metric that is agnostic to the balance of the data, which I'll talk about more in the next slide. Hyperparameter tuning was done with random search with cross-validation, and notable results were achieved with the random forest classifier, cap boost classifier, and the XG boost classifier. We ended up selecting random forest classifier for our production model. And then the advantages of this model is that it's lightweight, so it's good for something like the AWS Lambda function, and it's robust with imbalanced data sets. Our AUC ROC score was 91.3. And what this means is it's the area under the ROC curve, and it can be interpreted as the probability that a day grid with fire will receive a higher risk score than a day grid with no fire. In general, the data that we have collected through this data pipeline and the damage pipeline, it can be collected for really any country, and thus we are confident that with the right enhancements, our application can provide value to forest fire managers, not just in Canada, but in the whole world. And that concludes our presentation. Thank you.